My name is Travis, and thanks for listening. My research work this summer has been focused upon the study of 3D printed electrodes obtained using a PLA carbon black electrically conductive filament as a starting point for developing reproducible, low-cost electrochemical sensors. The objectives of my research project involved optimizing activation conditions for electrocatalysis and electrochemical Raman studies, optimizing 3D printing conditions, we use horizontal and vertical H and V to define them, and the preparation of a series of blueprint electrode designs along with the analyzation of their electrochemical response using cyclic voltammetry under varying potential scan rate conditions to be able to estimate the electrode's electrochemical surface area using the Randall-Sevchuk equation. The, the surface of the electrodes were also analyzed using scanning electron microscopy, Raman spectroscopy, and profilometry. Details about material equipment and software I've listed here but won't go through due to time. I prepared a series of electrode designs with the bulk of my studies being carried out on the second and third blueprints, B2 and B3, shown here, the difference being the amount of CBPLA, 50 millimeters being in the B2 generation, forming the entire electrical connection, while only 6 millimeters and a brass rod we inserted down the length for the B3. The Raman spectra gives no indication of PLA, only the typical D and G bands as expected for carbon black. The SEM spectra were taken before and after 24-hour treatment in sodium hydroxide of 0.5 molarity. Electrochemical studies were carried out in a conventional 3-electrode cell with a platinum counter, silver chloride reference, and carbon black PLA as the working. The studies were carried out using a 1-electrode reversible redox couple of 0.5 millimolar ferroferricyanide and 0.5 molar potassium chloride as the supporting electrolyte. Cyclic voltammogram on the left shows the B2 electrode design comparing 4 samples, its results indicating the 24-hour treatment in sodium hydroxide successfully acted to speed up the electron transfer at the electrode surface, shown by the large increase in current compared to untreated samples. I also compared varying durations of time for treating the electrodes in sodium hydroxide, with the results indicating increased current with increased duration, but we settle on 48 hours as the optimized conditions due to material degradation. Results are in good agreement to those obtained in other groups' work, confirming sodium hydroxide treatment leads a higher amount of uncoated CB due to PLA degradation through a saponification reaction. The SEM results correspond to this. The Randall-Sevchuk analysis, all samples studied show a linear relationship between peak current and the root square of the scan rate, as expected for an electrochemical process under diffusional control. The bar plots on the bottom correspond to the current density and delta E plots respectively. Sample size for B2 is 10, that for B3 is 5. The results show an improvement in reversibility for the B3 design with the brass wire, an expected result due to lower electrode resistance. The B2 designs show very high current densities, likely indicative of increased CB surface area after sodium hydroxide treatment, but more studies are required to gain more clarity on this conclusion. To conclude, our best results were obtained by the horizontal configuration showing higher current densities as well as better reversibility. However, results comparatively are not statistically different after normalizing by the electrochemical surface area for the B3 design. I'd like to acknowledge Richard Drake and Tanya Shimabukuro, who'd handled the 3D printing, Dr. Irakli Eberlich for the SEM and profilometry analysis, my supervisor, Dr. Liliana Trevani, my friend and advisor, Muna Abdulaziz, Ontario Tech, NSERC USRA. Thank you very much.